Hey everyone, it's Phil from SPEXcast. Just a heads up on this next episode, there is a little bit of reverb on my voice and one of our guests. We're still working out the kinks in our audio setup, but it's a great episode and I hope you enjoy. Episode 8, Telescopes. You're listening to SPEXcast. Welcome to SPEXcast. My name is Phil, and I'm here with TJ today.
Hello.
And we'll be your hosts for the next hour of your life. It's Astronomy Week here at RIT, and today we'll be speaking with two professors and astronomy experts about how we observe the ever-mysterious realm of our night sky. We're talking about telescopes. How do you like that intro? That's a new feature. So our guests are Dr. Jennifer Connelly.
Hey, everybody.
And Dr. Michael Zemcov.
Howdy.
And these two fine people are faculty members of the RIT School of Physics and Astronomy with PhDs in astrophysics and physics, respectively. Dr. Connelly's research focuses on galaxy groups and galactic evolution and performs some of her research at the RIT Observatory. Dr. Connelly is one of SPEC's faculty advisors and was also my astronomy professor last year. So, fun fact.
So everything that Phil says that's wrong in astronomy, I would like to say is not my fault.
Yeah, because I should know better.
Yes.
And Dr. Zemcov's research is focused on experimental cosmology and the cosmic background radiation. His recent projects have made use of suborbital flights using sounding rockets to observe the sky for short periods of time outside the Earth's atmosphere. Both of you have numerous publications that I cannot list because it would be way too long, and you do really, really interesting work. And thanks so much for coming on the show with us today. How are you guys doing?
Good to be here.
Great, yeah, thanks for inviting us.
Also, before we get started, I just want to mention that as we're recording this, like 5 minutes ago, SpaceX, their Falcon 9 first stage, landed on an autonomous drone ship in the middle of the ocean and didn't blow up. So,
or fall over.
Yeah, props to them.
That's tough.
Yeah.
They did it.
They finally made it look easy.
So unenthusiastic. It is. It's awesome, and I just wanted to give them a shout out.
Yeah.
Okay, so telescopes is a huge, really broad subject, and I just want to talk about all the cool things that are involved. And to get started, physics classes tell us that optical telescopes work by taking in a huge field of view and bend the light waves through lenses into a tiny area that's the size of our eyeball, so we can see things really far away. Right? Is that correct?
Mostly not live. So we don't always use lenses anymore to bend light. We now use mirrors to reflect it, but...
Yeah, so I was going to ask...
Basic principle, right.
So Galileo's telescope was a thing of glass that kind of refracted the light in a way that made things look bigger, right?
Yes.
Okay. So can you give me some details on how today's telescopes work? How do the mirrors bouncing light around take an image and make it zoomed in so much that we can see stuff from millions of light years away? Basic stuff.
Well, I'll say first, be careful about introducing the topic of magnification, which is where I think you're leaning here, and kind of blowing that out of proportion. No, okay, pun intended. So what most modern optical telescopes do is instead of using kind of Galileo's idea, they use Newton's ideas. And you hopefully also heard about that stuff in physics class, I hope.
Probably.
They're not nodding as enthusiastically as I'd like. But in general, what you're going to do is you're going to take an aperture, some opening, to let the light in.
Right.
And then the light's going to come in, and it's going to bounce off of a mirror. And then usually it goes up to another mirror, and that mirror will either take the light and go out the side of the telescope, kind of out the optical tube assembly, as we say, or back through that primary mirror.
And all these mirrors are curved, right?
Yep. All of them are curved to lesser extents and in slightly different shapes, depending on how everything's arranged.
How big are these mirrors? I mean, it depends on the telescope, right? But
yeah,
if you have at the RIT Observatory or even down to a small satellite-based thing, is it all just mirrors?
Well, no. You can make them sort of arbitrarily small, and people do science with very small telescopes. I do, I've done science with 7-centimeter telescopes. And then they get big. I don't know what the latest is. Do you? I mean, it's 10 meters, something like that in the optical, and then in the radio you can make them really big, 100 meters, bigger than that. Even.
So a mirror 100 meter, like
yeah, but it's not an optical mirror. It's not a shiny thing, right? It's aluminum shaped to look like a parabola or something like that.
Okay, because it's not. It doesn't have to. Not all telescopes look at visible light.
Exactly.
Right.
So the radio telescopes are like the huge one in where is it? Chile?
Arecibo?
I think so. The one that's looks like
in Costa Rica?
That's Costa Rica.
Yeah, that's Costa Rica.
Arecibo in Costa Rica.
It's huge, right?
And China's building an even bigger one in the ground, similar to that.
And aren't
Arecibo array.
those like meshes of?
Yeah, because radio waves don't care about holes in metal. The wavelengths are so long, they don't see that.
Oh wow! So it just bounces. It doesn't.
Yeah.
It's too big to go through the mesh.
Yeah, it
the
doesn't
whole
pass through the mesh. Yeah.
That's awesome. That leads into my next question. I have written down, are sensors relatively the same for different wavelengths of light? This is kind of different. This is about the sensor that I'm asking about. So we're not always looking with our eyeballs because we can't see radio waves. And we definitely don't want to see X-rays or gamma rays with eyeballs.
No, that's generally a super bad idea.
Right. So when the light, what does the light hit when we want to take a when we want to look at visible light, when we want to look at microwave light, when we want to look at gamma rays? What is capturing?
Well, it varies, right? So almost uniformly, there are exceptions. What you do when you detect light is you're converting it from electromagnetic waves into pushing electrons around some way or another. And so all detectors, well, not all detectors, most detectors share that in common, that you're doing something where you're wiggling electrons in some way. But the details of, how you do that depends on the wavelength, because the wavelength is the energy, and so different energy regimes require you to move electrons around different ways.
Yeah, so for a lot of optical detectors now, we take silicone. And when our optical photons hit the silicone, they knock off electrons. And then we read that as a voltage, and we convert that to something that the computer can read. And
Is that a similar principle to solar panels? Aren't those silicon waves?
Yes, it's very similar. Yeah.
Yeah. So we're moving the electrons in predictable ways, and then we teach our computers how to interpret those signals as whatever.
yeah, we do an analog to digital conversion, as you do in many, many other areas of detection.
Right. And what does the RIT Observatory use?
We have a brand new shiny CCD camera that we just started. So charged couple device. So it's not all that dissimilar from what you probably have in your smartphone. So we use relatively simple, well-known commercial grade detectors here at RIT, because our telescopes aren't terribly big. Mm-hmm. The one we use for most of our research here is a 12-inch telescope, so not huge, but we can do a fair bit of science with that. And considering the fact that our observatory is not in the darkest or highest place,
right,
it's good enough for us.
What things can you observe from Rochester?
A lot of the work is focused on variable stars, so stars that their light is changing over certain time periods. And there are lots of different types of those systems. We also look at asteroids. Sometimes we look at some of the brighter exoplanets. Mm-hmm. We don't look at the planets themselves, we watch them transit their stars. And we look at supernovae. So those are the big projects that we tend to focus on here.
Awesome. And is there a similar type of sensor in the sounding rockets that you use, Mike?
In sounding rockets, they're related to that. In fact, it's a different detector material, and then you bond that to silicon, because semiconductors are good for this kind of thing. But then you go out to other wavelengths, and I've worked at a lot of wavelengths and built instruments. And at longer wavelengths, you tend to get into a situation where you have to measure the temperature change of the photons coming in. So you've got basically a very sensitive thermometer, and you're looking at the light deposits a little bit of energy, and you see that temperature change, and that is your signal. And then at even longer wavelengths in the radio, you get into looking at how diodes behave and things like that. They're changing kind of the electric field in something, and that's how you detect it.
Is there the thermometer type detector? What are those called?
They're called bolometers.
It sounds so cute.
Well, I mean, it comes from Greek, and it basically means that they capture all the power. So if you put a bolometer, in a room and shielded, it would detect all the radiation falling on it because all the photons interact and change the temperature. In reality, you don't want all the light. You want some narrow range so you can make a picture. So
is that only feasible in space to use a bolometer, or can you build it?
We use them on the ground all the time. You have to cool them very cold because you're looking at very minute temperature changes. So we cool them down to 70 thousandths of a degree above absolute zero to get our signals. And that's hard and expensive, I guess, but that's what you have to do.
To give you a frame of reference, we cool our CCD here at the RIT Observatory to about minus 20 Celsius.
Yeah, which is still pretty cold. Do you have to cool it?
Cold enough.
Do you have to still cool it in the wintertime?
Some nights the cooling system is not doing much to maintain that temperature. it might have to just
And then when you get into things like gamma rays, which are very high energy particles, everything gets really weird, and you start basically building bricks of stuff and then looking for big energy deposits in it, and it becomes more like a particle detector.
Scintillation.
Yeah.
Interesting. Yes, the scintillation of the gamma rays. Yes.
So the only point there is that there's a bunch of different regimes, and you have to tune your technology for what you're trying to do.
Okay. TJ, do you have any questions about?
Yes, so I'm really interested in X-ray telescopes. I've looked at a couple diagrams of the Chandra X-ray satellite, and also the Japanese Hitomi satellite that's currently tumbling.
Sorry.
Would you like to go into a little bit about the Hitomi mission?
I don't know if I'm ready.
You're not emotionally prepared to talk about it?
I'm pretty upset. So my thesis work was comparing optical and X-ray observations. So I used a lot of Chandra data and a lot of XMM data, and I was so excited about Hitomi. And so many people, I was really excited, and especially because I'm teaching this artificial satellites course, I was like, this is perfect, and we're going to talk all about it. And the first data was fantastic. And now, she's out of control, basically.
Do we know
We're not sure yet. We have some theories. Some involve things like little explosions.
Yeah, little explosions in space are never a good thing.
Yeah, they don't end well, basically ever. And it's really hard to control a satellite as it is. But at the moment, it's tumbling. It doesn't look to be recoverable, but I never like to predict the death of these things before the end, because we've pulled out some pretty impressive recoveries, to be honest, over the years.
Part of the fun of deep space telescopes and deep space satellites and things.
Yeah, but the next X-ray scope is not due to launch for a while. So this is kind of going to leave a hole for us X-ray astronomers in terms of new fascinating data. And it would have been a huge improvement over existing facilities like Chandra and XMM, which are really kind of at the end of their life cycles.
How old are those set? Yeah, how old are they?
I'd have to look up the launch dates. I don't remember. Do you remember, Mike?
It's got to be a good 15 years.
Yeah, I was going to say 10 to 20, that window.
Yeah.
Are most space-based telescopes designed for very, very long service lifetimes? Like Hubble's been up there forever,
They're not designed that way. So a few years is kind of an average mission length, I think, for most space telescopes.
Do they design it for a certain set of observations, and then after that people are like, how can we use this telescope to do more research?
Yeah, so pretty much all of these scopes have kind of a primary science goal or set of objectives. And once those are met, then other priorities usually come to the forefront. But I think both Chandra and XMM have gone well beyond their original expectations in terms of the science.
Rosita's going up soon, right?
Yeah, soon is a relative term when you don't have anything else at the moment.
Okay.
Yeah, I'm looking at the data sheet for Chandra Ray, and it has a planned mission length of 15 years, and it's been 16 years, 8 months, and 16 days that it's been up there giving out data. So you designed for getting data for a certain period of time, and when hopefully it lasts to that or beyond that. With the Mars rovers, their missions were 90 days, and I think we have them going for 6 or 7 years now, which is an insane amount of
it's already there.
Mission life. Yeah, exactly.
Like, spent all the money.
You hope it works for those 90 days, and I think you get out of that. There was the Kepler telescope, right, that had a failed gyroscope for their original mission.
2 reaction wheels, right?
Yeah.
Yes, and they actually redesigned the control algorithm to use solar radiation pressure. And so they actually got additional service life out of it. And I was reading an article today about they're doing, still using solar radiation pressure, they're doing microgravitational lensing experiments. So they're looking at how the gravity of stars and galaxies bends light of stars behind them. And they're actually looking for exoplanets.
Awesome. That's another success story of space travel and whatever. Do you have any more questions?
Especially with the Mars missions, you think of, I think the rovers have been huge successes, but for a while there it was kind of hit the planet, get a prize. I mean, we had so many failed missions that it's, for those who've been in the field for a while, I think they have a greater appreciation when these things work out long term. Now I wonder if we're just setting the bar too high, and people always expect things to go well beyond their planned mission length, but oftentimes we also get some really impressive recoveries, which is always great to see.
You do get things that are like, not to the day, but pretty close when they're going to run out, especially when cryogens are involved. So I was involved with a space telescope called Herschel, which lasted a little bit longer than it was supposed to, but not dramatically. And once it ran out, and it's basically junk now.
Is that because like the nitrogen or whatever is cooling the sensor down, kind of boils off or evaporates or leaks through lines and things, and once it's gone, it's gone?
Yeah, because by thermodynamics you need to have something evaporating to keep the rest of the thing cold. So you lose material, and eventually there's nothing left. You're out of gas. Well, liquid, but.
And sometimes they're you can get warm mission time, where you can do different science, but depending on the detector, that might not be possible.
Do you have any more questions, DJ? I've got a whole page.
Oh, no, just continue.
Okay, I wrote another. I was feeling, philosophical when I wrote these questions down, so I've got another.
No.
Okay, get ready. Let's put on the dramatic music. Deep space is a lot like the oceans here on Earth. There's a lot going on out there, but observing things is difficult. We've discovered some really strange and unexpected biology at the bottom of the ocean. What's the weirdest or most unexpected thing you've observed in deep space? Or that's been observed, maybe not.
I was going to say personally?
Yeah, I mean, both. What's the coolest and weirdest space thing out there that you've seen?
Okay, the sounding rocket I was most recently involved with, that's now at the bottom of the Atlantic.
Back to the ocean.
Yeah, right. Yeah.
Full circle.
We were looking at basically how uniform is the near-infrared background light. So you ask, all the stuff in between the galaxies that you see should be black, but it doesn't have to be black. It could be that there's stuff in there and it's just very faint and hard to see, and most telescopes don't have big fields of view, so you can't see the ripples and the structure in that. So we built a sounding rocket to go look for that structure, the light between galaxies, and we saw a big signal. And we scratched our heads and we thought maybe we did something wrong, and then we compared against some other people's measurements that were at similar wavelengths, and we did formal cross correlation, and we saw the signal still there. And it took a long time, but eventually we convinced ourselves that what we're seeing is the light from stars in between galaxies. So when you build galaxies, you have little ones and they smash together and they make bigger and bigger ones, basically. But that process is messy, right? When you smash stuff together, a lot of it comes back and builds a bigger galaxy, but some of it just goes off to, who knows where. So we figured that actually there's a lot of light there. There's a lot of material there, and it's just really hard to see because most telescopes, you're not really sensitive to it in the right way. So that was a big surprise, and it took a long time to convince ourselves that was what we thought we were seeing.
And that's really interesting, but at the same time, I don't know, it's unsettling that the emptiness is not quite empty.
Oh, I find that comforting. I don't know about anyone else.
But what if,
I would find it light from stars in between makes me feel better. The rogue planet sort of thing, where we've got a system, the idea of a system all by itself.
Yeah.
That is unsettling to me.
Yeah, I read an excellent book by Isaac Asimov called Nemesis, which is all about a rogue planet that basically goes to the solar system and changes all of the orbital dynamics of the system and causes chaos. And being an Asimov book, there's a whole bunch of political kind of ideas and thought-provoking stuff, but just the physics of that, of this planet that people go to for exploration and refuge, ends up, coming back and destroying the Earth and the solar system. Very intimidating.
Yeah. What if we were like looking out and instead of seeing the Milky Way, we just saw the nothingness that you looked into?
Yeah. So
Exactly.
an interesting question is, what is, these stars would have planetary systems, one would presume. So you could imagine that we have a solar system like ours, but it's not attached to a galaxy. And so, speaking of books, there's a book by Ian Banks, who's actually one of my favorite authors, called Against a Dark Background, that's about such a planet.
Wow.
And spoiler alert, they the whole shtick is that they have to. There's a lot of politics and violence and stuff, but the overarching thing is that they want to go to the nearest galaxy, so they have to hollow out a moon and then fire it at the galaxy, and it's going to take them 1 million years to get there, so they have to be self-sufficient for that time. It's kind of fun.
It's a great read.
Do you know if there are any stars in between us and the next galaxy over? So, assuming that we develop technology to traverse our own galaxy, and we want to go to another one, do you think there's stars in between that we could hop along?
Well, I mean, galaxies have halos, so yeah, there's stars out there.
What do you mean by halos?
Well, so you think of a galaxy as kind of a pancake.
Right.
In fact, it's more like a crepe. It's very, very thin. But there are scattering processes that cause things like rogue planets, but also rogue stars. And there's a big diffuse ball of light. And so what I was saying about the sounding rocket thing before is that we figure there's more light in that than people thought, on average, in the whole universe. Because it's hard to measure, and really we only have a good handle on it for Milky Way, but Milky Way is only one thing, so it could be weird somehow.
Yeah, and the halo's fascinating. You get some of the oldest stars that we know a lot about right in the halo of our own Milky Way and these globular cluster systems. So, it might be cool to hang out in a globular cluster for a while.
All right, I have some other questions. This is more general in terms of observing and astronomy, and that's, can you guys talk about how, like, things like Kepler and things, we're analyzing planets that orbit around other stars, sometimes like light years upon light years away, and yet we hear about all these things like, oh, this one has water in its atmosphere, and this one, like all these specific things. I understand how we can kind of observe that they're there, because that seems like a much greater effect upon stars, But as far as specifics, how do the planets not get drowned out by their home stars?
So a lot of times they do. And a lot of what we know are really broad strokes about these systems. So one of my favorite kind of possible future telescopes is called the ATLAST telescope.
Is that the acronym?
ATLAST, which is the Advanced Technology Large Aperture Space Telescope. And it's going to look, if it ever comes to pass, for what are called biosignatures. And so usually what we're looking for are spectroscopic sort of fingerprints in the light and the elements of the atmospheres of these planets. But that's maybe 2030s.
So right now, are we just guessing based on, okay, there's this star, and we see that there are certain elements showing up in the spectrum, right? we're seeing that this type of star shouldn't have these elements here, so it must be a planet with this atmosphere?
So we do have some direct imaging of planets, and those you can get a better sense of what their atmospheres look like specifically. You can also kind of see them peak out if they transit and they kind of start their cycle. You can just get the atmosphere of the planet as it peaks out. So that's another way that we trace what elements we think are present.
Cool.
Yeah, those are very hard measurements.
Yeah, I can imagine.
Yeah.
So there are a lot of challenges with building telescopes on the ground. The atmosphere is kind of a big soupy mess that blocks a lot of those photons that we like to look at. So building telescopes in space is a great way of getting past a lot of that interference. How do we build telescopes either in space or telescopes on the ground big enough to get a lot of that information from the light waves?
You brought this topic up.
Oh, okay.
This is
a
your
big
jam.
question. So you build a telescope for space basically the same way that you build one for the ground. Some of the time you take advantage of the fact that space is a vacuum, which lets you do things like, when your gas of your cryogens evaporates, it automatically goes out and that's an easier advantage because on the ground that isn't necessarily the case. All the optical tools and detectors and everything are pretty much the same. The one big difference is, like you mentioned, you've got this big soupy mess of atmosphere at many wavelengths. What that does is it means your detector sees more photons. Those photons come with random arrival times, which we call shot noise. And that means the brighter the background of what you're looking at, the more noise you have. So in space, one of the main advantages, in fact, is that this noise isn't there. Because whatever is hitting your detector is astrophysical, and usually that stuff's faint. So we take advantage of that and can make much more sensitive measurements because we don't have that extra component of noise. So that's a big difference in space, and that's one we take advantage of very often.
Though we do have to deal with more cosmic rays.
But isn't that what you research is cosmic rays? Like
No,
X-rays?
I don't research cosmic rays.
What's a cosmic ray?
What's a cosmic ray?
Yeah, what
How
do
would
you mean by that?
Oh man, Phil, were you not in my class?
I don't like terminology. I'm not good with vocab.
Oh, I see.
I
So-
can spell.
So X-rays, right? You're familiar with that. You've probably had an X-ray in your
I
life, or you've
believe
seen,
so,
or you've
yes.
seen, have you seen that
Perhaps.
sort of thing? So how energetic is an X-ray?
Lots.
Lots. Could you guess? Like, let's talk electron volts. Let's get a little
I passed the
scientific
class,
for a second.
okay? I passed.
I know. or let's talk kind of temperature. How hot?
We could do a fact check on that.
Google
I
it,
can
Google
tell
it
you.
before she tells us.
Okay, I'll let him Google for a second, but it's like a million, like 10 to the 6 Kelvin. All right? Now, you see X-rays from all sorts of sources in space. And generally speaking, you can track back where they come from. Cosmic rays are kind of universal noise to a certain extent. And so they're high energy particles as well, but a bit different than X-rays or gamma rays or those sorts of things. And the thing with the being above the atmosphere is you get more of them in your space
Because
telescope.
there's no atmosphere to save.
Because more of them get to you. We get them on the ground all the time, and it's something that in your images you have to kind of clean those or deal with those in a different way. So you get more of those in space. But the other thing is we've gotten really good at adaptive optics on the ground. So all this atmospheric turbulence, we're getting better and better at dealing with that. But for a lot of wavelengths, we can't see them from the ground at all, like X-rays. So that's where it gets good in space. We sometimes have to do interesting things to get big mirrors. The James Webb Space Telescope, which is going to launch relatively soon. Yay. It has kind of a jack-in-the-box feel to it, in that it can't launch with its mirror all in the perfect alignment. It also has a great sun shield, which is like the size of a tennis court or something, something around that regime. So in space, sometimes you have to get creative and, okay, how do I pack this? And then how do I unpack it remotely? We're getting better and better with that.
So that brings up the question that I think TJ was asking too, and can we assemble a huge telescope in space like we assembled the space station, or like on the ground there's SETI, which is an array of telescopes that all work together. Is it infeasible to just launch a bunch of parts or a bunch of individual pieces of a telescope and arrange them in space and engineer something bigger than could be launched from the ground? And is there any project that's like trying to do that near term?
I mean, you could. I haven't heard of anything that is. That seems really hard.
And that is hard in what sense? The fact that everything needs to be so precise and.
Yeah. I mean, how do you assemble? Okay, so I either need astronauts or robots. Astronauts are.
We've got both of those.
Well, astronauts are very expensive to get into space, and robots are dumb. So I don't know. You could. It just sounds expensive.
And do you think the cost is what's prohibited more sort of serious looks at that? Like, is money the main limiting factor here?
Well, again, I think from the ground, because we've got adaptive optics and we've gotten better and better at solving so many of the issues that we have in the ground, it's so much cheaper. And to a certain extent, we've kind of hit a limit, at least in the optical regime, when you compare cost benefit to, all right, well, we can fix these things from the ground. We have these problems that we don't have in space, but we can fix them relatively easily, or we can deal with them. So why bother launching the optical telescope?
Because it's cool.
Because it's cool. Oh, I wish, Phil, that I could get funded for just because it's cool.
Yeah, the biggest obstacle, it seems, is definitely cost. There is a class of U.S. defense spy satellite called the Orion satellites, and they have a 100-meter radio telescope diameter, which is huge.
Like an equivalent?
No, actual. 100 meters in diameter. And that's all because they managed to fold up the antenna, and that fit inside the normal fairing of a Delta IV Heavy, which is a big rocket. But the engineers can get everything to fit in that small space. Mm-hmm. Now, we're talking about $1 billion plus for that one specific satellite. And what you end up having is that you can build a much larger telescope and fix the issues on the ground for the cost of building a huge telescope in space.
So I do know that there's some research here that's very, very preliminary at RIT, where they essentially, you can think of sort of spraying your mirror. So you take tiny little hemispheres, like something the size that you'd get maybe out of a spray can. And if you can control them, you can make as big a mirror as you want. That's, I think, pretty far down the road, but what a cool idea.
What about things like CubeSats? Like, those are relatively inexpensive mini telescopes. You can launch a bunch at once.
It's tough. Yeah, I mean, you could imagine doing things with that. It would probably look like, an interferometer of some sort. But the problem with CubeSats is it's hard to fit stuff in them because they're so small. The telescopes, they're sort of irreducible in size.
What do you mean? Like some components, like
so with the CubeSat, right? Like the 1U is 10 by 10 by 10 centimeters, and so you're automatically going to be looking at a 3U or a 6U for any useful like optical tube, and you need very fine pointing accuracy if you're going to be doing astro observations. So you're going to want control moment gyros inside. You're going to want the telescope, the detectors, whatever cooling systems you're going to use.
Needs to go somewhere.
And it pushes the upper bound of like the CubeSat standard. So you can definitely do it on like a 3U or a 6U, but you're not going to get the quality and the resolution of a 50-pound satellite, which is it's still a very small satellite in the scheme of things, but breaks you out of the Lego box CubeSat world.
Right. So you can just might as well launch a bigger telescope.
Well, so this is something my group's trying to do is CubeSats with telescopes on them, but you're stuck doing very niche science. You can't be a Hubble. You can't do everything to everyone.
Right.
So that's the trade. But
Yeah.
it's inexpensive.
Yeah, and the Atlas telescope that we were talking about earlier, there are 2 different mirror designs for that. One's an 8 mirror, one's a 16 mirror. I have no idea how, meter. I have no idea how they will do the 16 meter.
That's pretty big.
Yeah, and it's having to definitely assemble things in space.
And for all these space telescopes, we're talking about low Earth orbit, right? Or are we talking about like Lagrange points? Are we sending them outside the solar system? Would it be useful to send something like past Pluto because there's not as much light from the sun?
Yeah, that's what we're trying to do. It's really great because it gets you out of the obscuring solar system stuff that is a problem at many wavelengths.
Could we use the satellites that are already way out there to like just point them in a different direction?
Even a Lagrange point is still near Earth. Okay. And there's no reason to go past a Lagrange point unless you're trying to go to a planet. Some planetary missions have it ends up, what's a camera for a planetary mission? It's a telescope.
Right.
So they're very capable, but they're usually not built with astronomy in mind, so they have things that aren't quite good.
Right.
Plus it takes a really long time to get out there.
Yeah. And to kind of communicate with it.
Yep.
I forget what it was, but maybe Voyager or something. It sent it took one picture of Neptune or something, and it has to send tiny bits of data over a really long period of time. So I can just imagine having a telescope way out there if you want anything of high resolution or something like that.
New Horizons, which went past Pluto just a while ago, New Year, I guess. How long was it in the Pluto system? 24 hours? It's going to take them more than a year to telemeter all the data back.
Wow.
Yeah.
Now, part of that is because they want to do other things in the meantime. Like, they want to look at other stuff. But still, all of these things, it's not just a matter of getting out there time-wise, but getting that data back.
Is that one of the reasons why we keep them around Earth? Or is that just kind of when you're talking about really far away, that's one of the things you have to consider, and here we have the luxury of not worrying about it as much?
Well, Hubble's a good example of why being in low Earth orbit is not a bad idea, because if something does go wrong that's a fixable thing, you can go fix it.
Right.
Yeah. The largest gain is getting outside of the atmosphere, and then there are specific cases where, going to Lagrange point or sun-synchronous orbit or even to another planet is beneficial, but just getting out of the atmosphere, you have a huge gain in signal to noise.
Mike, you were going to say something?
I forgot.
Do you think we'll end up building telescopes on the moon?
Sure.
It's something nobody really talks about. At least I haven't heard things. We want to build colonies and bases. I
was talking about this with somebody the other day, and it ends up the moon is a terrible place for optical telescopes.
Why?
Because it's dusty.
The dust is awful. And it's really abrasive, and it just gets everywhere.
And it looks like it's vacuum, but in fact there's kind of this hazy dust that's just floating around just above the surface.
Like from an impact, it goes up there and
takes long. Apparently it's very dusty. It has an atmosphere basically, but it's just very tenuous. But a radio telescope, we don't care about that. It would be great because then you get on the far side of the moon. You don't have to worry about things like cell phones and TV signals and what have you.
It's a natural dampener of all the noise.
Right.
But then how do you talk to it? A satellite or relay or something?
Yeah, relay.
Yeah.
That's not hard.
Okay. I tried to do that in Kerbal Space Program, and it was pretty hard for me. But
well, I think by the time we're worried about actually building telescopes on the moon, we'll have that figured out.
Okay.
But yeah, radio's the way to go if you're going to build it on the moon.
Is there...
So, one last question. With X-rays, we talked about a little bit your basic optical tube and using mirrors and whatnot. But with the mirror arrangement in X-ray telescopes is rather unique. And so I was looking at the Chandra lens setup. Could you kind of elaborate on how the Chandra uses that and future applications for X-ray telescopes?
Can you talk? Are you looking at a picture or something? I'm not familiar with the internals of this specific telescope.
So with the Chandra, I'm not an expert in this, but from what I've researched, in order to focus X-rays, you have to have a very slight angle of incidence. And so basically you have concentric mirrors, and so you have a long tube. And so the X-rays will enter, and they will refract slightly off of these mirrors
Very, very
and then be
slightly each
focused
time.
down. Is that correct?
So they're kind of these nested parabolas. They look very, very different from an optical telescope. And that was a big problem for a while, especially interpreting the data. You talked about images earlier, and X-ray images are a little more difficult to work with, but we've gotten quite good at it at this point. So all the major X-ray observatories are designed with this kind of nested parabolic mirror.
Right.
And as TJ rightly said, this you want a really small angle of incidence. This reflection angle has to be very small.
Yep. And so what are the are we going to continue to launch X-ray satellites with that? Does Hitomi have a mirror like this?
Yeah, but far down the line, they're talking nanomirrors, which I'm just now learning about, but sounds really fun. The problem with these telescopes is as you disperse the X-rays, you also absorb them. So for Chandra, for instance, you only detect about 1 out of 10 incident X-rays. That's pretty big loss. So they're looking at these teeny tiny little tightly spaced silicone wafers for the next generation, future generation, I should say. Not the ones that are planned, but kind of planned to launch, but ones down the road.
Right. That's so weird. It's weird, super weird. Telescopes are kind of, I don't interface with telescopes regularly.
You should come to the observatory, Phil.
I should. TJ's showing me a picture, and it looks like if you took a thing of aluminum foil and kind of unrolled it just slightly, so there's a bunch of
Yeah.
really
That's a
shiny
great
stuff
analogy,
Yeah.
wrapped around each other. Is that what it's like? I mean,
No, but that's what
really quick, I have another question that I really want to ask, but there's a related one that I wrote down, and that's how do we detect things that can't be seen, like with the rogue stars or even the, dare I say, Planet 9? Things that do you just look out in a spot in a way that we haven't looked that way before? Like,
yeah, that's usually how it goes.
and then everything else is by accident?
Well, I mean,
How do we?
it's physics, right? So you design an experiment that should be sensitive to the thing you're looking for.
Right.
So if you're looking for Planet 9, you're basically saying, okay, I know how fast it needs to be moving, and so I'm going to look where I think it might be based on some other inference and match my telescope, and then all the stars will be smeared. So I'm looking for a thing that isn't smeared. That's how usually they do that kind of stuff. That's one way, but then all the other things you just asked, they're all different, right? You know, how do we know there's dark energy in the universe? Well, that there's a couple different lines of evidence for that, but they're all like customized in the sense that it's a very specific question you're asking, and you do a very specific experiment to see if you can see it.
Is it very easy to go so long without ever observing a certain thing? Like, we're looking up at the night sky every night. We're in space with telescopes that are constantly observing things, but is it that easy to miss something like a planet?
Well, planets are small. They're puny, right? And if they're far enough away from us, then absolutely. The sky is huge. Space is big, yeah, yada, yada. But if you're looking for this tiny little dot, essentially, over, and then it's moving slowly, right? Because if it's far away from us, it's probably not going very quickly
It's not going to be
either.
very bright because it's far away from the sun.
Super dim. Then yeah, I mean, you gotta have something to work with, and if it's not giving you many photons, then it's pretty easy to miss it. Now, with the whole Planet 9 thing, what they've done is kind of tried to get orbital constraints from how other things are moving in the area.
Right.
To say, okay, we think there's something that's kind of this big over in that direction. If you look at how much space that actually covers, how much sky you have to cover, it's a lot.
Yeah. Cool. Okay, this is the question I wanted to ask. Can we make telescopes, like deep space telescopes where we're looking really far away, that use something other than light to make the observations? And if they already exist, what would we use? Can we use gravity waves?
I was going to say, you might have heard a recent discovery in the news. Quite exciting. LIGO is on the ground, but there's a mission now called, I think, ELISA, which would take gravitational wave detection to space, which would be amazing. And I think ELISA, somewhere I actually wrote down, ELISA, each arm of that detector is supposed to be something like 5 million kilometers long.
Whoa. And how are they doing that? I'm not familiar with ELISA.
Very, very carefully, Phil, is the right answer to that question.
I mean, lasers and telescopes and really accurate pointing.
Yeah.
Exactly. Well done. Yes.
Yay!
So we did on a previous episode interferometers and going into how LIGO works. And basically the principle is that instead of building underground tubes in the ground where you have earthquakes and cows trampling and all this interference, you put that out into space, and you do have huge engineering challenges for the actual satellites. Pointing lasers very accurately, knowing exactly where the satellite's pointed and whatnot. But once you have that pointing accuracy, then you can move things very far apart with very little interference between them, and that can make that interference pattern at the end of what you're looking at much more clear.
Right, and the further apart they are, the more sensitive it is, right? Is there anything other than gravity waves and light that we can use to detect?
Sure. So in the course I'm teaching right now, which is radiative processes, the very first thing you say is all the ways we learn about the universe, right? And light is probably the most obvious one, but if you think about it, asteroids are direct pieces of stuff coming from space, so they tell you a lot about space. And likewise, particles of various sorts. So protons get accelerated to very high energies, and we can either detect them directly, or we look for their effect on the atmosphere. People build telescopes that are looking for what's called Cherenkov radiation, which is basically that these particles are going too quickly in the atmosphere, and they have to radiate light very quickly to decelerate so they don't violate the speed of light. And so it's out in Chile or somewhere like that, right? They build these big water detection things that are looking for particles from muon showers, and also optical telescopes, and they can kind of back out where these protons are coming from. And likewise, neutrinos. People build these big tanks of water and things like that deep underground, and if you are very quiet and wait a very long time, you can occasionally see neutrinos come and hit your detector. So all these things are teaching us things about the universe.
Yeah, and when we say we're looking through telescopes with all these sensors, are we actually getting images, or are we just getting data that we can interpret as a thing out there?
What is an image?
A bunch of pixels on a screen.
Isn't it data that we can interpret to tell us about things out there?
But do you get?
Are you asking about pretty pictures? Or
I think
I'm not blaming you if you are.
Pictures. So we've seen a lot of really great true color and false color images from Hubble and other space telescopes. Do you get a data set that is like a specific wavelength of that false color image, or are you looking at
Is it just like
each individual pixel?
Is it just like a spike on a scale that you're like, oh, there's a spike in this frequency, therefore, yeah, I just proved my thesis.
Yeah, people do. We call them single pixel experiments, right? If for whatever reason all you could afford is one spatial element, but you're looking spectrally, yeah, you can get some time trace.
And you can still make observations just from one spike or one pixel.
Sure.
What type of things would you find that way?
I mean, for a long time, that's how we did it. We had kind of these photometers that were equivalent to one big pixel, and then you just counted how things changed over time. So time series, I mean, that's very important in most applications in astronomy these days.
Right. Is that like when you were looking for a planet around a star and you're looking for a change in the brightness, that's the type of brightness over time graph?
So that's one example. Anything that varies works, right? Anything. Now, when we're actually looking for planets, we're not using single element detectors like we're talking about right now. But in the earlier days, a lot of those detectors were similar to what you're envisioning.
Cool. And I have 4 more questions for you guys, and they're fun. Brace yourself. Are you ready?
I'm psyched.
Let's go.
Okay, so seeing older light that originated very far away allows us to effectively, in air quotes, see into the past. Is there anything we could look at that would let us see into the future? Because time is a construct of the human imagination, right?
A crystal ball.
Yeah.
I think that's kind of our job in a way, at least a lot of us in astronomy, is that we're trying to use what we can see about the evolution of the entire universe and individual structures and project to see what's gonna happen. For instance, when people talk about, okay, how will the end come, right? Okay, other than we better get off this planet before the sun expands too much. Besides that, what will happen to the universe itself? And the things that we're trying to understand using this information about what's happening now in the universe and what happened before is going to indicate to us how it will all end.
Is there anything that we can directly use?
Well, even with the sun expanding and consuming the Earth, like right now when we look at the sun, it's in the middle of its life and it's making light and we're all happy and life goes on Earth. But because of the different telescopes in astronomy, you can look back so far at different stars. We can see stars at the beginning of their life, at the end of the life. We can see supernovas. And so by looking at all of these different kind of reference points, we can then kind of model what our sun will do in the future.
So yeah, that's all true. That's all about physical modeling. But there's fundamental uncertainties here, right? It ends up that reality is basically quantum mechanics, or so physics says, right? And one thing about quantum mechanics is if I start dorking around with what the quantum fields are and the details of how that works, I can make them unstable. So I can set up a situation where protons, let's say, have been stable for the past 13.6 billion years, but they don't have to be. I could flick a switch that has to do with the decay of some other quantum field that we don't know about, and protons could become unstable and everything disintegrates in a flash.
Oh.
That's one solution.
and there's hundreds of ways to do that to a universe. So, it's good that we're doing physical modeling and we can project that forward, but there's a large degree of uncertainty when it comes to, it's like predicting the stock market. Past performance doesn't guarantee future returns.
Right.
We are pretty certain that the sun, for example, is going to behave the way we think it is, though, because it's not a quantum system.
Yeah, when you say uncertainty, you mean like not even like we're 99.99999%. Like we're sure of what we're observing is true and real, but not necessarily what we predict is how it's going to be.
Well, I mean, here's one we're trying to figure out now, and I don't know how it's going to pan out, but there is a fundamental degree of uncertainty, which is it's this dark energy thing. It looks like the universe's expansion is accelerating, and it's accelerating in such a way that everything gets further from itself pretty much exponentially. And then people call this the Big Rip, and eventually things become so far apart that light can't propagate between them, and the universe gets very boring and very big and very empty.
Depressing.
But we don't know that for a fact, because the thing that dark energy is governed by a quantum field, and it could be doing anything it wants. We don't know. We have to go out and measure it, and then come up with a theory that explains what it might be and what it might do.
Cool. Last question for you guys, and that's, I don't know if you've listened to any of our show, but in episode 5 we talked to Brendan Ireland, who's a researcher at the CCRG, and we talked to him about wormholes. So wormholes are possible, but they're really unstable. You couldn't fly a spaceship through them. Could we point a telescope through a wormhole and look across the universe? Like, could we use them as windows rather than doorways?
Yes.
Have we ever observed
No.
a wormhole?
The next question is,
We
is such
just-
a thing as a wormhole?
Yeah, we just found more evidence for black holes. Give us some time.
So, futurology here. What if we had a huge thing that could make wormholes? Could we use that as a telescope? Like, pointing to places?
Yeah, but why wouldn't you just go there?
Yeah,
Because it would
got
collapse
that.
on you.
Well, if you've got the technology to make the wormhole in the first place, I bet you could figure that out.
Hey, give them time. Flipping your words back on.
Yeah,
Episode
that's
500.
That's interesting. I have to read about that. I hadn't heard that you can't pass matter through a wormhole.
Well,
You can.
it's just
I thought you could.
You can.
it's very. He said it was very unstable. Like
Yes, I could believe that.
Yeah.
The problem is the metric is so steeply curved that whatever you sent through would get turned into mashed potatoes.
Chunky
I like
salsa.
mashed
Chunky
like chunky
salsa.
salsa.
Yeah. There's a great
Do
book
you
called
like
The Physics
yourself
of
as chunky salsa?
No. There's a great book called The Physics of Star Trek, and it talks about warp drive, and it talks about the need for these shields because if you don't have them, everyone turns into chunky salsa.
Gotta have those inertial dampeners.
Yep. You got it.
We're working on that too.
Physics is fun until it's inconvenient.
Yeah.
Then you dampen it and ignore it.
Yeah. All right. That's all the questions I had. Did you have any more, TJ?
No, I think we're good.
Okay. Thanks a lot, you guys, for talking with us. This has been super fun and super awesome. Sorry for all the weird and maybe not so scientific questions.
I think we're probably used to the weird and wonderful as astronomers.
Yeah, that's yeah. And thanks for having us.
Yeah.
And once again, that's Mike Zemcov and Jennifer Connelly from RIT. Thanks for listening. We'll be back next week with another discussion on space exploration, science, and technology. If you'd like to share your thoughts on telescopes, astronomy, or if you have requests for another discussion topic, send an email to SPEXcast@gmail.com or tweet to us at RITSpecs. If you want to hear more, consider subscribing to us through iTunes or your favorite podcast app. All past episodes are also available to download from our website. This podcast is made possible by RIT Specs, a space exploration student faculty research organization at the Rochester Institute of Technology. Special thanks to the Interactive Learning Grant Program for giving us the tools to promote student-faculty engagement outside the classroom. Our music is by Kevin Hartnell. This has been SPEXcast. We'll see you next week.